Good morning, I'm so excited. It's already day 15 of Advent of Code. This is Anagon Live and welcome again and thanks for joining the stream again on the 15th day of Advent of Code. We have 15 minutes left and yesterday I ran a little bit short on time and I wasn't able to finish part 2. So I would like to do a quick recap of yesterday's puzzle and to tell you how I solved part 1 and also part 2, which I did off screen yesterday. So yesterday, for those who have done the puzzle, they know it. For those who haven't, yesterday we were dealing with a chemical reaction and it's called stoichiometry. I have no idea what that means. But basically what we were doing is we were trying to produce fuel out of ore. And from ore we can produce several other chemicals. And then after that we have to combine those chemicals together with other chemicals and to produce fuel in the very end. So it's kind of like a big chain of reactions and there are a lot of dependencies, and the question is of course how much ore do you need to produce fuel in the end. So what you get basically is you have one fuel as an output and a lot of stuff goes into it, like A and B, but to get B you need C, but to get B you might also need A, and there might be another D, and there were also some interesting dependencies where E is required to produce A and D also, but E is also required to produce D, so all kinds of links. But there was one rule, and that rule is every element can only be produced by one single reaction. So for example, you cannot have the situation where C also produces A, so A is already produced by something else. Then secondly, part of that reaction list that you get is how much you need of each element to make the reaction work. So for example, to produce a fuel you could say that you need 7A and 1B, for example, and that it would produce one fuel exactly. Well, those ratios could be different every time, so you might have that 3A and 5B together produce 8 fuel, let's say, or 8 of another chemical. And so if you need, for example, a specific amount of fuel, let's say 2, or let's say you need, well, I'm talking about fuel, but of course most of the reactions aren't about fuel. So let's say that we have a reaction with A and B producing X, and you need it at one point exactly 3X, but your reaction produces 2X, and for that you need 2 A's and 1B, for example. Then you need to run the reaction twice, and that means that in the end you're going to have 2 X's going there, another times 2 X's, but for the second reaction you only need one of those. So in the end you're going to have 3 going there, and then you're going to have 1X left over. And since there are so many reactions and all of the elements are able to be reused in all kinds of different ways, that means that you're going to need to reuse this extra X that you had from your reaction as a leftover. So in part 1 you need to take into account all of that. You need to take into account what if what I need right now is bigger than the amount provided by my reaction. That means I have to run the reaction a little bit more. And also, how do you deal with the leftovers? So that's right here. And that was quite a lot of administration to take into account. And there are different ways to solve it. So basically what I did is, let's say I have a needed list. It's like an ingredient list, you could say. So I have here a list that says I need 1A and 1B, or 2 B's, and here I have available. And let's say I'm producing one too many of an item, then I would just add it here in the list as one available. That's what I did. Some people have done it in different ways. Some people have done it, for example, by keeping only a needed list, and if there's something available, then they would just remove it from the needed list or subtract it. I'm not sure if the needed list can go negative. Maybe that's possible. That means that you basically have a little bit of extra space to take elements as you go, executing all of those reactions. So let's have a look at what I did. And hi everyone who's online, by the way. Do say hi in the chat. Let's see, good morning. So what I did is, hey Fuzzy, good morning, how are you doing? So I was reading the input, and the input, by the way, looks like this. So it's basically a list. Like here it says you need 164 ores and you get 2 TJ, TLJ, well, it's like just random letters basically, and it's not really important what those letters mean, as long as you know that each chemical is produced by one reaction and you can find each of them somewhere else. So you see that this chemical is on the right hand side of one reaction, but on the left hand side of all of the others. Fuzzy, you're saying you like the backdrop? Thank you very much. I worked on it yesterday, and I'm also very happy with this new setup. There was one more thing, that is ore. Ore is the very origin of all of the reactions, and it cannot be produced. So to produce fuel, you need to start with some ore. So the question is, how much fuel do you need, how much ore do you need for producing one ore? How much ore do you need for producing one fuel? That's the way. So what I did, I'm splitting the input by the arrow sign, and then I'm looking at the left hand, it's the ingredients, and I'm splitting those by commas because we have multiple of them. I did make a little function. Hey Alex, good morning, how are you doing? Welcome back. I'm just explaining part 1 right now, how I did it and what the puzzle was about. And so I parsed the ingredients by splitting on spaces, so that I get on the left a count and on the right an element. As you can see here on the right, a count and an element. And after getting all of those ingredients on the left hand, I'm going to iterate over them so that actually I parse the ingredient on the right first, and then I go over all the kind of ingredients sections on the left and make sure that I parse them into counts and elements. Have you managed to do part 2 using your idea yesterday? I did finish part 2. I'm not sure if my idea was in its full stage when I finished, and we did look at your solution for part 2 yesterday already, so I know you did a binary search, but I did try to solve it without binary search, just to still kind of exercise my brain and thinking. So I solved it without binary search, and I'll show you in a few moments how I did that. We have, okay, so I parse the input ingredients, and then I'm making a big list of reactions. So this is going to contain the output element as an index, and the value for the dictionary is going to be how much of that output is produced, and a list of ingredients that you need to produce it. So for part 1, we are running the function getOreNeeded for one amount of fuel, and to do that calculation, we first say we have nothing available. It's a dictionary where we keep track for each element how much we have of it and how much we need of each element, and we start by saying that what we need is a certain amount of fuel, which is 1 by default, and I do keep track of this kind of grocery list twice. Once I do it in a dictionary to easily look up the amounts that we need for each item, but I also keep it in a list, and that is because the order, I thought the order was important. I wanted to yeah, the order, I'll explain why that was important to me. So let's say we have a reaction that says A and B results in C. Then I want to, after figuring out that this reaction exists, I want to continue with A and then afterwards with B, and not just B, for example, because if B needs something else like C and C needs D, and if we're always starting with the last one, that means that we're going to go very deep into the reaction chain first before, well, I guess we're going deep into the reaction chain anyway, and it's either a choice of going the left way or the right way, or left, right and left, depending on how you look at it. And I wanted to go left hand first, so that I could easily debug my code and kind of follow along with the elements from left to right. So that's why I wanted to have a list that I could use to always pop the first element from. So we say that we need 0 ore because we need to keep track of how much ore we need. That was the puzzle's first part's question. So we need 0 ore, and then as we go and we find out that we need some ore at the end of the reaction chain, we're just going to add that amount here. So as long as we still have some elements on our grocery list, on our needed elements list, then we're going to keep running reactions. And the first element we need is here, and in the dictionary we look up how much we need of it. And if the needed element is not in the reaction list, then we're going to continue. And that means that if we need ore, for example, let's see, actually, what is that about? The needed element is not in reactions. I think I made that for the case where we have ore as a needed element. Yeah, because that one doesn't occur in the reaction output list. So we are looking up the correct reaction to produce the element we need, and that is done here. And we get the input ingredients from that, and we get how much is produced by that reaction. So here is all of the administration. So we have a certain amount already available, and that is here, but our reaction produces some amount also, and so we're going to see how much are we going to use from the available amount, and what we're going to use is whichever is lower. So if we have more available than we need, we're just taking what is needed, and if we have more than needed, no, if we have less than needed, then we're just going to use all of it. So what we're using from the existing stock is the minimum of those two. Then we need to keep track of how much we still need after taking items from the stock, and it's how much we needed minus how much we're using from the stock. So that's still needed, and still needed is the basis for determining how many reactions we're going to need to run. So if we still need some items after looking at the stock, we're going to calculate how many reactions we need to run. And that is basically how much is produced by this reaction versus how much we need. So if we need 2 but we produce 1, then we need to do 2 reactions. And if we have some kind of odd ratio where we get like 1.5 reactions, we're just going to round it up, we're going to do 2 reactions. How much do we then produce if we run it such amount of times? It's the reaction count multiplied by the output count. How much do we have left over? Again, we have to look at all the imbalances between needed and produced. So we produced 2 per reaction. No, let's say we produced like 5 in total, but we needed 3, then we're going to have 2 left over, and those are going to be added to the available list. Then we have determined how much we keep in the end and how much we used, but we still need to process all of the reaction's input elements. We have less than 2 minutes left, so I'm going to go very quick. I might explain part 2 after the puzzle is released. So the needed input count is multiplied by the reaction count, because if we run a reaction 10 times and this particular reaction requires 5 Bs, then we're going to require 50 Bs for that. And that's it. And if we are needing ore, then we're just going to count it because we don't actually produce ore. And otherwise, we're going to say that well, this element we needed such amount of, and let's keep it in our needed list, in our shopping list, so to say. And if our input element is not in the input, in the needed elements list, we're going to append it. This little condition is so that I don't add it twice to the same list and that I can process it all at once. And I think we don't have enough time to explain part 2, but very quickly what I did is I know how much fuel is needed, how much ore is needed for one fuel, so I just divided the amount of ore that we have by the amount of ore per fuel, and then I multiplied it by 2, and because I know that reactions are going to be more efficient, so I'm going to start with a kind of guess a little bit too far out, and then I'm going to decrease my guesses less and less until I reach a point where I actually can produce fuel with the amount of ore that we have. That was it. Day 15 is starting. I wish everyone good luck, and when you're finished, do come on the stream. Today I'll be streaming for about 2 hours, so we do have time to look at your answers and hopefully to solve both parts. Good luck! Day 15, Oxygen System. Out here in deep space, many things can go wrong. Fortunately, many of those things have indicator lights. Unfortunately, one of those lights is lit. The oxygen system for part of the ship has failed. I learned in the year ago that those lights are called idiot lights or something. Just a light that says that something is wrong, but it doesn't actually tell you what is wrong. According to the readouts, the oxygen system must have failed days ago after a rupture in oxygen tank 2. That section of the ship was automatically sealed once oxygen levels went dangerously low. A single remotely operated repair droid is your only option for fixing the oxygen system. The Elf's Care package included an encode program for puzzle input that you can use to remotely control the repair droid. So we have another droid that we can control, cool. By running that program, you can directly direct the repair droid to the oxygen system and fix the problem. Remote control program executes the following steps in a loop forever. Accept a move command via the input instruction. Send the movement command to the repair droid. Wait for the repair droid to finish the movement operation. And report on the status of the repair droid via an output instruction. Okay, so there are 4 movement commands understood. The directions of the wind. Any other command is invalid. The movements differ in direction but not in distance. Okay. In a long enough east-west hallway, a series of commands like 4444, 3333 would leave the robot droid back where it was, because you go 4 times north and then... Why exactly? Hold on. If we go east, 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 and then west, 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 yes, okay, then we're at the same position. Okay. The repair droid can reply with any of the following status codes. 0, the repair droid has hit a wall, the position has not changed. 1, the repair droid has moved 1 step in the requested direction. 2, the repair droid has moved 1 step in the requested direction. Its new position is the location of the oxygen system. I think we're going to have to do a kind of search, like a search algorithm. You don't know anything about the area around the repair droid, but you can figure it out by watching the status codes. For example, we can draw the area using D for the droid and hashtag for walls, dot for locations the droid can traverse, and empty space for unexplored locations. Then the initial state looks like this. To make the droid go north, send it 1. If it replies with 0, you know that the location is a wall and the droid didn't move. To move east, send a 4. A reply of 1 means the movement was successful. Okay. Then perhaps attempts to move north 1, south and east are all met with replies of 0. Now you know the repair droid is in a dead end. Backtrack with 3, which you already know will get a reply of 1 because you already know that location is open. Then perhaps west gets a reply of 0, south gets a reply of 2, and so on. Okay. Now because of the reply of 2, you know you found the oxygen system. In this example, it was only 2 moves away from the repair droid's starting position. What is the fewest number of movement commands required to move the repair droid from its starting position to the location of the oxygen system. Alright, so that means that we're going to have to do a breadth first search. So it means that not just any solution is correct, but we have to find the quickest solution. And the most important thing for that is that we explore depth first search, that's breadth first, excuse me. So how we can visualize that is that we have a starting point called S, and there are different ways to go from that starting point. And there might be quick ways to reach the oxygen tank and not quick ways to reach it. So let's say here we have an oxygen tank, but actually one of the other paths also leads to the oxygen tank like this. So to know for sure that we have the quickest solution, we need to actually look at all of the paths breadth first. So we have to go layer by layer, so to say. And to go layer by layer, what we need to do is when we are checking positions, we need to always add the new positions that we're going to check at some point in the future to the end of our checking list. So we have a kind of list like to check, and we start of course with position S, and then from S we're going to find out that we have A, B and C as options. And first we're going to add A, B and C, and then we see that we haven't found the oxygen tank yet. So, and then from A, B and C we're going to look at E, F, G, H, I and J. So that means that when we just finished checking A, we're going to add E to our checking list, and we're not going to go directly handling E, but we're going to continue with B. So that is how it looks. So we have a checking list, and now there's something important that some of those cases might end up being the same. Like for example the J, which has the oxygen tank, that is basically the same node as this node, which also has J. And the reason you can have multiple nodes is because if you have a maze, I'm thinking of this puzzle as a maze, and it looks like this, and your oxygen tank is here, and you're starting here, let's say, you can reach that tank by going this direction, but you can also reach it by this direction. And so we don't want to test this node twice. No, hold on, actually, that is not so much the big deal. I guess once you reach the oxygen tank, it's not the problem. The problem is rather that if you have the oxygen tank a little bit further, like here, then you're going to reach this node twice, this one here. And if you've already reached it through one point, then you don't need to look up all of its children again, like this child, for example, the second time you reach it. So you need a needed, not a needed list, but a visited list. So that is the basis of our algorithm. And then the question is, if you have found a node, what are you going to do with it? Are you going to keep track of it? Are you going to keep track of the number of steps? I guess we also want to keep a number of steps. So we have visited here, and for each node we're going to say how many steps it took. So A was 1 in this case, and let's say we reached E at some point, it was 2 steps. Well, that's it. And then if we finally reach the node where we have the oxygen tank, then we have actually found it, and we can take the number of steps as the puzzle's part 1 solution. So let's download the input for today. Here we go, day 15. Time is passing so fast. We've already done 14 puzzles out of 25. That means that after this one there are 9 to go. Is it 9 or 10? I guess 10. One off errors are so bad. So we make a Python file. Just like every day I do it in Python. And we're going to start by reading the input. And I'm not sure if I want to make test cases today. I think I have a clear picture of what I'm doing. So I'm just going to do it this way. Well, you know what? Let me do it the right way this time. With a with statement. With open input.txt. And we're running it from the parent directory for historical reasons as file. And we're going to split this entire file, I think. Read lines. We only need the first line and we can split it by commas. And then we get the... Oh, hold on a second. I'm not sure why I'm doing this. Actually, this is an int code program, so we just need a computer. That's all we need. We have int code for day 9. That's the latest version of it. And we're going to load a program. Load from file, day 15 input.txt. And then we're going to run it. Run program. And what was the instruction again? We're going to... How do we control the program? Well, by running the program, you direct the robot droid. And this is the steps that you do. Accept a movement. Send the move command to the repair droid. So basically, we need to provide an input here, like a direction. And let's say we start by going north. And we have the directions. Where are they? North, south, west, and east. North, south, west, and east. I do like to create sort of constants for all of these magic numbers so that I don't have to think about it. So let's say we start by going north and then we run the program. And then we need to... hold on. Accept a move command via input instruction. Send the move command to the repair droid. Okay. That's what we did. Wait for the repair droid to finish the movement operation. So let's run program. Report on the status via an output instruction. So I guess the output is already provided automatically. So I don't think we need to give it any instruction. Let's see what happens when we run this. And we get, of course, all of the debug code, the debug statements from the computer. And I'm going to disable that for now. I have to put it after initializing it, of course. And it says 0, so that means, in this case, what is the meaning of that again? It is written somewhere. 0. Okay, that's written here. So 0 means a wall. And success is 1 and goal is 2. Okay, so we have our list. This is going to be the loop. So that is going to be true. It's going to loop forever, so until it's done. And the output for the computer is going to be written there, and we can just pop it. Just pop the first position. Status. Yes. And if the status is the goal, then we have finished. But then we can break. And we can, let's see. We need an XY coordinate also, so I called them ABC and so on in my drawing here. But of course, those nodes are identified by their coordinates. So S can be 0, 0 relatively to where we start. And this could be, for example, 1, 0, and this is 0, 1. And this could be 1, not 1, 1 actually. It could be 0, minus 1, and then we have another one, minus 1, 0. Those are the options. So we have a 2 checklist. let's call it check visit, yeah, like this, and visited. And visited will be a dictionary where we can keep the distances to all of the visited nodes. And we'll start by let's see, how do we start? We start by toVisit equals we start with position 0, 0. I guess that's how we are gonna do it. It sounds a bit odd to kind of say where your starting point is, but you do have to have a starting point, and I don't want to deal with the starting part of the algorithm differently from any other part, so we'll just use the visiting list for that. So what's the first thing we need to do if we visit a node? There's always two questions with search algorithms. Do you first check if you are at the goal position, or do you first check the children? And it depends a little bit on your problem, but in general the rule is first you check for the children, and then you check if you are actually are in the goal position. And the reason is that if you have, let's say that there is a cost to every path, and in this case it's not like that, but let's say you have a graph that looks like this, and this distance is 5 and this distance is 2 and this is 4, let's say, then it is possible to reach the destination in this way, and it could be that that was the first way you found out about this goal position. That is even more likely to happen if you're doing breadth first search and your second direction also has an intermediate node, so it would be like this. So just from the fact that you reached your goal through this way doesn't mean it's the shortest way. So before you actually decide to break, you do need to check the other node on the level before and see if you reach it in a quicker way. Now, I think for this particular problem that is not going to happen, because all of the paths have the same distance, in fact. So if we would have another way to reach the oxygen system with the same number of steps, it would also be the same distance and it wouldn't be more costly. So I think in our case we can actually really just break if the position that we're at is the goal. But I do now realize also that what I was explaining is mostly helpful for situations when you have a grid, like say like this. Show it right here. Let's say you have a grid and you know your position and you need to go to 3, well, I'm just making up a number. Let's say you need to go to 3, 2. Then all you need to do to check if you're at the right position is to check the coordinates. But in the case of our robot today, we cannot actually check directly if we're at the goal. We first have to go there, to go somewhere, and then check if we're at the goal. Okay, so we are at position 0, 0. Let's take our current position, and that is going to be from toVisit, and we're popping the first item. I see Stavoy, you've already finished. Stavoy hasn't been in the chat for some time, but he's doing very well. Always one of the first to finish. He has his own Twitch channel, so you can also have a look there later if you're interested. I have something fun, you know, I have star awards when you finish the puzzle, and I'm going to show how they work right now. And I just need to do a little bit of clicking for that. And like this. Yeah, so that's what it looks like. And unfortunately with the streaming software you sometimes have to reload a scene so that it wouldn't kind of crash and never work anymore. Okay, so we have our current position and we're going to add all of the nodes that come after it to the list. And the nodes after it are, of course, all the different directions. and I'll call them deltas because I'm going to take to use like actual like dx dy deltas to indicate every direction. So we have north, south, west and east. Maybe I can actually use a dictionary for that and make it even more explicit. So for each of these I'm going to uppercase them, but we don't have a tool for that, so I have to retype it, but I can use this. So there we go, and then if we go north, that means that we're going 0 to the left and 1 up. South means 0 and 1 down. West means 1 to the left and 0 vertically, and east means 1 to the right and 0 vertically also. So let's say we have all those directions, and then for each direction, and we want to iterate over the keys. So for direction in, direction deltas, we are going to append that particular direction to the to visit list. So new position, or to visit position is actually the current position, which is position, and we're taking the x and the y of it, and then to that we will add the direction value. Maybe we can actually use items and get both the direction and the value. Like this, dx dy, that's even possible in Python, destructuring multiple levels deep. That is super handy. So now we have our to-visit position, and we're going to add it to the to-visit list. Like this. And then we're going to run the computer on... Wait, we're not going to run it on each direction, because we're just appending it, and then in the next iteration we're going to actually visit that location. Okay. Now, what do we need to keep track of? Yeah, I'm thinking now, so we visited all these locations, do we need to keep track of paths or anything like that? And it seems like we don't, but we might need to do that for part 2. So all we need to keep track of to kind of continue exploring a certain area is to know where was it and how many steps did it take to get there. So we run the program and we give it an input, we give it a direction, and the current direction we're going to go to, hold on, So how do we know which direction we're going to actually go to? Okay, so actually I do realize that our strategy is not complete, because normally I would say, okay, just go to 10,3, like x is 10 and y is 3. And then the next time we'll just say, okay, now let's say we are there. But we're not there. We have to actually tell the computer to go there by going in one of those directions. And what it means is that we do have a state, and the computer, the robot, can only be in one position at once. So if we are going to do a breadth first search, that is going to be very hard actually, because to do a breadth first search with a robot that has only one location, it's going to look like this. So we have the starting position, and we have 4 children, and then we have another number of children. That means that we're going here, and then we're going back up and going here, and back up and here, and that up and here. And then if we want to go to here, which is the first node in the next layer, we actually need to go back up here and then here and then here. So we're kind of like doing this over and over, and that's going to be very slow. Well, if it was a really a physical robot, it would be very slow. So I'm thinking now if the breadth first search, as I was thinking about it, is the best idea. It's not what you would do if you had an actual robot. You would of course explore until you hit a dead end and then just keep exploring everything that's not explored yet. And besides that, I'm not sure I have a good idea how to go back to our previous layer in the exploration tree after trying every position. Well, we could of course just say, okay, we could take a copy of the robot. So basically we make a copy for each position. That means that if we are visiting a location, we're just gonna make an entire copy of the robot. That could be huge. I'm not sure. The good part about the robot is that its state is basically the instruction pointer and the input. So the input is quite big and we are going to visit a lot of nodes, so probably copying everything will be very slow, or rather memory intense. So copying doesn't seem like a good idea, but maybe we do have to actually keep track of where the previous position was, so that we can go back if it didn't work well. Okay. Let's see how we can do that. Okay. I'm going to draw a little bit more because it's not so clear yet what the right way is to do that. So we have our needed list. Well, we call it to visit, and we have visited, and we're starting with S, and we say that we reached it in 0 steps, so that's something I haven't done yet. And S is here, and then we're going to have a few options to visit. I'll just use 2 as an example. We have A and B, so we'll add it to our list, A and B, and those will take 1 step. It's like 0 plus 1. It's 1, and this also is 1. And now let's say that we are at A. Finally, we made the move to A and it was incorrect. Hold on. How can we actually know that it's correct? So let's say that we have finished this part and we've added A and B to the list. And we've already calculated how many steps it takes. I think that is something we can do in it right from the start. And now we're dealing with A, so it means we're here. And we're going to explore. Let's see. That means that we're going to look at its children, and those are, let's say, C and D. And we're adding those to the list. C and D, and they have 2 and 2 as the distances. But C turns out, well, you know what, let's, okay, so yes, C and D are actually appended to the end of the list, but we need to know if A actually is the goal position. So we check the status, and status is nope. Let's say it's empty. Then we need to go back. So to go back, here we have A, and how do we know how we can go back? So after checking A, we need to go back to S and make this jump. And basically what we need to do is keep an entire path of how we reached A so that we can go back to its parent node. So its parent node is going to be S. So instead of keeping track of only the number of steps, we also need to keep track of the parent nodes. And technically speaking, we can keep track of only one parent and do a kind of recursive lookup from there. But I don't want to use the toVisit list for that. Ah yeah, and actually I'm making a little bit of a mistake here. Those steps are not going to be saved in the toVisit list. They're going to be saved in the visit list. So S is visited with 0 steps, A with 1, and so on. B also with 1. And then we can keep also a pointer from A to its parent and from B to its parent. And let's say we have C, that is also a child node of A, then C will actually point to A, and then we can just kind of look it up step by step, just like going by like this. Okay, so that's that. Let's keep a list of the visited nodes and also keep track of the paths. So once we visited a position, it means we need to go there, but for the case of the first position, we haven't moved, and the first, let's see, if we don't provide any movement command to the robot, we're not going to get an output either. And I guess we have an instruction that the first position where we are is an empty position. So let's say that we are going to store that the first node that we visited was 0, 0, and it has no parent, and the status of that, yeah, we also, let's keep also a track of the status. The status is empty. Stavoy has finished part 2 also. Wow, so fast. Wall, success, and goal. I think success should rather be defined as empty, because it means that there is an empty space. Okay, so we're keeping track and saying that the first node is empty and it has no parent. Okay, actually I'll keep the state first and then the parent, and the number of steps was 0. And alright, like that. Okay, so once we know where we are, and we're going to look at all of the different possibilities of where we can go. But technically speaking, it's not like we're going to be able to visit specific coordinates, but rather we are able to go certain directions like north, south, east, and west. And that's a little bit different because actually once we decide where we want to go, we need to know how we're going to go there. So instead of keeping track of positions, I want to keep track of the direction we're going to go to. So instead of a single direction, I will actually... Alex, you've already finished. Nice. And that was part 1, and now part 2 is left. So we're keeping the direction that we want to go to. And we kind of also don't want to go in the direction where we just came from. To do that, you can either look at where are we now, and then where were we one step before, and let's not go there. But also what you can do is to keep track of which places you visited, and then check that it didn't exist in there yet. So we have the position, and if our toVisit position is not in the visited positions, in the keys that is, I'm going to write it explicitly because I keep forgetting if we're getting keys if we don't write it, or if we're getting values. So like that. We're now 30 minutes into part 1 and still working on it. It takes a little bit of time to understand the problem correctly and all of the little aspects that are involved. So the toVisit position is not in the visited positions, so then that means we can append it to the toVisit list. And is not in. Okay, that's a little bit too natural language for Python to understand. Not in is the right way to write it. So then we're going to append it to the visited positions, and we're keeping track of the directions. That is important. So that means that our direction is determined by the toVisitList, like this. And so basically what it means is that the toVisitList is actually the location from where you're going to explore and not the target location. Yeah. Okay, so basically it's not like we need to visit location 00. We are already there, but what we do need to do is from there we need to visit up, down, left and right. So it will look a little bit different. We can use the direction deltas for that, and I'll rename it to directions like this, so we can say that, well, hold on a second, do we want to keep track of the position where we were at the time of visiting? Maybe we do, not entirely sure. Oh yeah, well, it's basically that's already the key right there. So no, that is the visited list. The toVisitList at this point only has the position, but we're going to do it differently. We're going to have a direction also. So hold on. From this position we need to go north. North is one of the ways we need to go. Okay, let's see if that makes sense. We need to go south, or maybe, yeah, let's do it in the same order. West and east. Okay, I find it a little bit confusing that I call it toVisit position. So 00 is not really the position we're going to visit. Actually, the position is going to be... Yeah, okay, I see. The position we're going to visit is actually the delta. So let's see if we can multi-cursor that. So we are going in the direction specified in the first part of the tuple, and then the position we're going to visit by doing that is specified in the second part of the tuple. Yeah, of course you could also store the position where you are right now instead, but I'm doing it this way. Direction from starting point and target destination is on the right part of the tuple. Okay, it's Sunday. I see that not a lot of people are online today. I hope that everything is okay, or maybe you're just having a nice good sleep because it's Sunday after all and you didn't want to wake up very early. But I'm here every day on the stream solving this live. Destination. So position, I'm going to make that explicit. Target position. Like this. First we're exploring the new positions that we can reach from that. And we're going to tell our robot to run in that direction. And to tell us what the status was, and then if the status is the goal we're going to break, and otherwise we're going to append. And let's have a look and also print our toVisitList, and we're going to print that we're visiting a target position by going up, going a certain direction, visiting a certain location, target position, and what are we going to print? We're going to print one of those as a name. And Alex, you've solved part 2 also. Nice. and that gives me a bit of hope that I can solve it too. But of course Alex is always very fast, so we cannot assume that I can do it in the same speed. But that means that Alex might come on and have a look at how I'm doing. So list index is going out of range because I have a direction here. And oh, hold on, I wanted to use strings here. Oh wait, actually we can do it like this. That's a very simple way to do it. Just use a string. So we have up, down, left and right, or maybe north, south, west and east, and then we're taking a direction from there. And we get an index out of bounds. Why is that? List index out of range. Our direction is... Okay, let's print the direction. It says it's 4. Yeah, 4 is not a valid direction, of course. So why do we get 4? Well, oh, it is actually correct. We just have the directions, they start by 1. So I'll just fix it like this in a simple way. So it's visiting a lot of places, and I have no idea what it's doing, actually. No idea at all. So maybe what we need to make it a little bit better is to make a grid, which is a default dict, which I like very much for 2D grids. And the default dict will return another default dict. And that one will return empty. And empty was this. And we can import it from the collections library. And so what it means that is after we run the computer, we get a status, and then we know a certain position was reached. And we can save that position into the grid. So the target position has an X and a Y. And we're going to store it in the grid at position XY, YX. I always keep grids row by row. So first you indicate the row and then the column. And the status, we write it like this. And then we're going to print the grid every time. So for Y in row, Y in grid.keys, and for X in grid Y, and or maybe we can do it like this. Items means that we get in Y, a Y in the row, and then we can also iterate over the rows items. It means we get an X and a status, and we're going to print status with no new line and printing a new line every row. That means basically just printing an empty character, and Python will append a new line to it automatically. But we cannot just print the status as it is, because that would be 0, 1 and 2. Let's print it a little bit better than that. So we are using status as an index, and we have 3 characters to print. So empty, 0 is a wall, and then empty, and then the row. So wall, and what do we have? Unexplored territory is actually a dot, or was it not? I think the dot was... Ah, okay. I see. So unexplored territory, we also need to model that. And so instead of saying empty everywhere, I'll just call it unexplored. And that is going to be -1. Maybe -1 is not the best number to use if you're using characters or character indexes. So the last one is going to be unexplored, and then the goal is going to be the circle, or yeah, maybe the star, and then unexplored is just a space. And let's run it and actually put a breakpoint there so that we can see what is happening. So our map looks completely empty right now, and I do also realize that actually we need to know how wide our grid is. We cannot just iterate over only the items that we visited. So let's also keep an X range and a Y range. So the Y range is actually the minimum of all of the Y coordinates, or let's call it min Y. Minimum of all of the Y coordinates, that is basically the grid keys, and the max Y is the maximum of that. That's of course not efficient, but I can always improve it later if it turns out to be too slow. And the min X is the minimum of all of the X's, and I'm going to see if I can use a double for loop for the first time in my life in Python. So we have Y for Y and row in grid.items, and then we want to also get all the X's out of the rows. So X for X, how does that work? S in row. Maybe like this. And that means actually we don't need S, we can just use the keys, and that's it. And why do we get not defined? X for X in row. Oh, maybe it's like this actually what we can do. So basically we return row for Y. Ah yeah. And then maybe we don't need to do... Oh, maybe that's how it works. So maybe we can leave out those brackets. That's basically what it is. So it's kind of like a nested comprehension, but you can just leave out the brackets. Then it's actually easy to read. I'll keep it like this for now. Make sure that it works the way I think it does. So we have the minimum X and we have the maximum X. This is not very efficient. So I'll really copy it into X's. Hans has already solved it. Good job, well done. We are now almost 45 minutes into the puzzle, and it does take a bit of work to actually get all of the things done. So instead of going over the X and Y positions that we have visited, we're going to iterate over the range. So we are going to go from Y in. Now we need to have a range, and that looks like min Y until max Y. And hold on a second, is that actually not Python? Python range between. Let's see how we do that. I know range starts with 0 normally, but we can say start and stop. Okay, so do we have an example? Right, okay, so let me just try it in the interactive console to make sure that we're including the last one. So let's say we start at 10 and want to end at 12. Now we want to have a list out of that. So the last one is not included, so we need to include it like this and use the range function. And for the X position it's the same. For X in range, minimum X, maximum X plus 1. And then the status on that position is actually the grid YX. And that can be also unexplored, for which we have a separate value. It says unsupported operand. What are we doing? Here something is going wrong. I think we might be looping over the wrong thing. So for X in row, that returns the row. Yes, that's correct, but I think I want to return the keys from the row. That is actually the positions, but it looks like that it's not entirely correct. Let's see, the X positions is called dict keys. I don't like that very much. I want to have it as a list so that I can read it very clearly. Okay, so actually the expositions, we kind of need to flatten that, and I'm not sure if we can do that easily. So we have now, for every row, we have the list of expositions. And we want to have a single row. And you can't do that, you need to actually use an append function. But itertools does have it. You can use itertools chain. Okay, so let's do that. So I don't need this part. Itertools. What just happened? It should be list itertools.chain, and then with this entire thing, then we should get like a nice clean flat list of x's. And yeah, that looks a little bit better than before. And it still says dict keys, so I do need to actually force it into a list. Ah, but that didn't work, and that's because I need to actually explode the list. Oh, wow. Look, it's running. It's already running. And I think there was a way to clear the screen. I learned it from Alex a few days ago, and I'm going to try to use that. I think it was system.clear. And I'm importing it? No, maybe it's called sys. Yeah. No. Let's look at day 13. That's where we use this function, I think. Let's see. Yeah, this is the AI code. Oh yeah, os.systemClear. Okay. So why I want to use that is because then you can get a little bit more clear output. And Arcanian Archer then told you about printing a special character. Okay. So if we print that one, it would clean the screen. And it reduces flickering but doesn't clear everything. Okay, let's look at the difference. So now you need to know that to be able to do this, this is a kind of terminal feature, special terminal feature. So it means that it can do more than simply appending text to the screen. It can also remove things from the screen. And for that you need a real terminal, not just an output console. So you need to emulate the terminal in the output console, and then you won't get those warnings. And now you see that our output looks different, but not the way I want it. And it's printing all of the visiting positions, and I don't want that. And we're printing a lot more than we need. Maybe... oh, we're still printing a lot more than we need. And where do we print it? Here, we're printing the to visit list. And now you can see what it's actually doing. And what you can see is... it looks like it's actually revisiting a lot of locations many times. So there's definitely some bugs here. And also I think we're not keeping track of the number of steps. We're also not keeping track of which places we've visited. But we're exploring, so that's the good part of it. And I do want to also show where the robot is. And I'm going to try Zarankiewicz suggestion to try this little method and see how that works. So on my screen it doesn't change much, but it does seem to run quite a lot faster, to be honest. It seems very fast now, and strangely enough we get different output, so I think that it is a little bit less reliable to use that. And if we use both together, maybe it's better? I'm not sure if it's better. Yeah, it does seem to jump around a little bit less. I'm not sure. I think it jumps around a little bit less. So let's keep it like this. So one thing that I want to do is... oh yeah, okay, the faster version only works if you're sure to redraw everything. Otherwise you'll still have old stuff left over. But I am actually redrawing everything, I am writing hashes everywhere, but it still doesn't write walls everywhere, as you can see. But maybe there's a bug in my code and I'm actually inconsistent in determining the output. That can be, of course. I want to show where my robot is. That's something that I think can help us to debug the code also. So I'm going to print like a block. I want to print, or maybe an at. We're going to print an at if the robot is on position XY. So we have XY for target position. Target position is the position that we ended up after running the program. Okay. So we have X and Y, and I'm going to use a different name here so we don't get naming conflicts. Underscore X. So if those two positions, those two dimensions are exactly the same, then our robot is there. We're going to print an at with no ending. And otherwise we're going to print something from the graphics library. And it's very fast, but actually let's just run it in debug mode. That would be a lot clearer. So we are at the start. We have explored up, I suppose, and let's also print what we're doing. So what we're doing, oh, we already are done. Why doesn't it say? It doesn't say anything because we're clearing. Let's clear at the start of the loop instead. And maybe let's not clear at all for the moment. So going north, visiting 0, -1, and it knows now that there is a wall. Okay. And I realized something. If there's a wall, we shouldn't actually look for nodes in that position. So that is, of course, very obvious once you see it happen. So if the status is not a wall, then we're going to append all the child nodes to it. Let's see what we're going to append. Appending to visit position to list. Okay. And because I know that this is a tuple, Python is going to try to apply each part of the tuple to a separate parameter in the format. So we need to actually wrap it with another tuple to make sure that that doesn't happen. And tuples with only one element cannot be written like this, and you need to write a comma with nothing after it, for those who are learning Python at the moment. So what happens? We're going north and we found a wall. We're not going to append any new positions to explore from there. And we're going south, and I want to know where we are. This is actually where we are at that position, okay? And that was also a wall, I guess. Let's write down on the screen what we found. So we found a wall. Let's actually make a little function out of this. And how shall we call it? Little method. Print status. Okay. And we can do that. And then here again, because we're working in global scope, Python is just not adding any of those parameters to the method. It's just reading it from global scope. That's something I really don't like about working with Python in PyCharm. So print status, print the status, and oh well, maybe I want to actually not print it but just return it. It's such a small function and almost not doesn't make sense to actually make a little function out of it. Yeah, it doesn't make sense to do that. Let me just copy this line as it was. So here we found like this. I'm adding brackets to be able to see empty spaces. We don't need print. Like this. And S should actually be status. So when we look at the very top, what do we see? No, it's already so fast that the start of the output is already gone. So we're going north and we're visiting X position 0 and Y minus 1, and we found a wall, okay. And then we're going south, visiting this position, we found a wall. And then we're going to the left and we found an empty space, so that is fine. And that means we're going to append 3 items to the list, and 1 item is not added because it was already in the visited list. That's pretty cool. Now for the next iteration we need to also append that one to the visited list. Because right now we're not doing that. I think visited is here and it's not used anywhere. So after we visit it we can say we have done so. Visited with the position that we were gonna go to, right? Because we use positions as indexes. Target position, that is visited, and we are storing there the status that we found. We are also storing the parent. I'm not sure if we can do that, because yeah, we can do that. We basically know the direction that we took. So technically speaking, well, the parent, maybe we can just store the direction that took us there as the parent. So let's do that. So the direction we took was this one, and then the number of steps that we took. And I'll say number of steps. How many steps do we actually have at that point? So we have to visit, and to visit doesn't contain the steps, but visited does contain the steps. And so the parent is actually the target position, and then we need to take the delta from there. Not sure if that's the way I want to approach it. Maybe let's first start with just keeping track of the direction and the status, and then see how we go from there. So we rerun it, and we have a visited list, and let's... Okay, I'm actually not going to print the visited list, it would be very big, but we can look at it in the debugger. So maybe I can actually split my view in such a way that I can see the output together with the debugger. Let's see how that could go. I've now lost my console, so that's not entirely the thing I wanted to do. This is not the console. And here we have some panels. Let's see how it works. Okay, now we have the console, and it looks like I'm not able to actually make that separate. No. Okay, well, we'll just do it this way then. Okay, so what have we visited so far? No, it's not so important. Okay, so we run another loop, and we found a wall again, and then we're going to go to the left. But it bothers me a little bit that we have not visited here. It should be empty. So basically the dots are for those cases where we have visited something and it is an open space. And I think the position where we start should also be like that. But for now we don't have that. I did write visited here, and here I'm looking at the grid, but basically I could have also looked at visited, the visited array. I think so, because the visited array has the status there also. So I guess I don't really need a grid. I just need to do visited and then the XY position and then take the first element out of that. That should work, and then we should also see a little dot at the beginning. That means in fact that our grid was not necessary. So here we go, and it says that we found a wall, and now everything looks quite bad. So I think that I rather stick with my grid for now, and then I just need to make sure that the grid on position 0, 0 contains an empty spot. Let's run it again. And now it says that I'm doing something wrong. Yeah, because actually our grid doesn't work that way. It works by really 2 separate dimensions. Alright, so we found a wall when we went down. And then we're going left. Oh, now I'm not sure how it happens that we actually show nothing there. Like show... You know what, I'm just gonna remove it and go back to the way it was. Let's run it. No, our code is now really different than before. So I did break something and I'm not entirely sure what, so I'm just going to undo a bunch of code. Until we get... it should be _x_y, that's why it was wrong. So we are running and we see that we have nothing. That's why the visited also didn't work. Of course, so we can do it like this. We just need to use the _x and y and then take the first element out of it. Now it should show up correctly. And we do have a key error because the coordinates are in the other order. A lot of small mistakes. Yeah, okay, now it looks the way I wanted it. And still I don't see other people having solved the puzzle yet. I think this might be a really tricky one and people might have decided to see if they can solve it later. So let's look at the global leaderboard and look at the statistics here. And okay, so we see that actually in the entire world only 293 people have solved part 2. That's not a whole lot. Usually by this time it's like 2,000 or 5,000, so it's really not that simple. And some users have finished only the first half. So, okay, that makes sense, then I don't have to worry why there are not many people online today. Also, it might be some kind of holiday, I don't know. It's 15th of December. In my country, where I am now, Belgium, there is no holiday today. And we get some exception because our visited array is not a default dictionary. Man. Okay, so if visited, let's keep a position like x, y, and if the position is... Yeah, maybe people want to sleep in on Sunday, right? But I'm already so used to it, so not sure if I could even do it. So if the position exists, then we use that one, and otherwise we are just gonna use unexplored. Yeah. I'm not sure, it looks like it should. Our console looks like this, and then we're going down and we find a wall. Then we're going left, we find an open space. And now I lost my robot. Why did I lose my robot? I'm not sure why I did lose it. We have x and y, and we're not casting it to integers. Can it be like that? This is the reason. Let's look at the next iteration. And so our position right now, it's -1, -1. And our robot's position is X and Y. And X is 1 and 0. Oh. Okay, yeah, that means that we're just not at the robot's position. That's fine. And then let's see if we ever print the robot, but we don't. That makes no sense, does it? Why don't we print the robot's position? We have a certain range, of course. So we're running again, and we have a range that goes from... let's look in the debugger. The X range. We don't have it. Let's just evaluate it here. So we have -1, 0, and 1. And for min X and max X, we have -1 and 1. So it's 3 by 3. And our robot is in position... What position are we? That's target position. The robot is in position -1, -1. Okay. That should be in the list. And I'm not sure why we don't see it. So we're evaluating every step now, and let's see if we get something. It says that it's true in this case. Oh, I'm comparing Y with X. That's why. That's why. It's Y and that's why. No. An @ sign. Very good. And we are going down, okay. And that's nothing, and then we're going left, that's nothing. We're going right, that's nothing. We're going up and it's nothing. But, of course, what our robot is doing internally and what we think it's doing is not exactly correct, because the way the robot works is that it has its own... Basically, the robot's code contains the map, and it's just going to tell us whether or not we find a wall. And what we're visualizing right now is not correct because the robot actually has to go first back, like walk every step back to the previous position to be able to explore the next point. And man, I don't like the solution to really go back all the way. Maybe we should really do a depth first search, but still, if we do a depth first search, it means basically exploring until you can't go anywhere and then go back. Then you're still going to have to trace back all your steps. And okay, so basically after visiting a position, we always have to go back to the previous position, but we can do that. That is actually not that hard. So we ran the program, we went somewhere, and then we visited it and we know the status. And then afterwards we are going to just trace back. Backtrack. So it would look like this. We calculate the previous position by taking the target position and then using the deltas, the direction, and making it the opposite. So the X and the Y was actually from all of the directions that we had. We just extract it, and instead of adding, we're just going to subtract. So the target position's X value minus the dx of the direction is the old direction, and the same goes for target position. So now we are basically back, but we do have to tell it to go back. But that's the absolute position. Okay, we actually don't have to tell the absolute position. All we need to do is to tell the opposite direction. So if our direction was north, we're going south. If it was west, we're going east. I would like to have the opposite direction always 2 after the previous one. I'm going to change my order so that I can just add 2 always. So south plus 2 is going to be north, north plus 2 is going to be south. That is very handy. So where do we go? So the opposite direction is the previous direction's index, and that is the direction's index? No. I don't know how to do that. I think it was find, wasn't it? No. Index. Okay, so there is a function called index, but my editor doesn't tell me. Because I'm targeting a dictionary right now. So out of all the keys, actually, I need to take the index of the current direction. And maybe I should make it into a list first. And once I have the index, I can do +2 and then modulo it by 4 so that we never get out of bounds. And that is the opposite direction index. And the opposite direction is going to be, let's say, we need to know the index is, hold on a second. That's the index, and now we need to get from that also the actual direction value. Maybe I'll just keep this one the way it was. Direction orders. Hey Arcanian Archer, you've solved part 1. That took a long time. I mean, it's taking me a long time. And it means that this puzzle was really quite hard. Because usually you're able to solve the puzzles much quicker. Me too, by the way. So good job for holding on and really going through it till the very end. So direction order. So we start with north, then west, maybe northeast, southwest. That's what we're going to use for reversing directions. So the opposite direction is basically when we have our direction order and we're looking up in that one, the direction, and then we're adding 2 to it, and we're going to modulo it by 4, and then we're going to take from the direction order that particular direction, and the opposite direction is then here, and then we're running the program, and then of course the output, we don't need to use it. Hopefully that's going to work. Let's see. It's running a lot. And let's see how it looks. So we're going down, and then when we're going to the... Where are we gonna go? We're going west from the starting point, that's still okay. And then when we're going to the east, we're also going from the starting point, and we find an open space. So you see now our output is actually different. And now we're popping from an empty list. And that is because what exactly? It means that at some point we didn't append anything to the to visit list. So we went south and found a wall. We went west and found a wall. We went east and found a wall. That looks a little bit incorrect. So let's see if we're actually tracing back to the opposite direction correctly. And we're going back to directions northeast, south, west. Actually I changed the order at some point, and I want to make sure that I reverted that. North, south, west, east. Yes. So north, south, west, east. That's where we're going back to. And I want to make sure that it is the correct direction. So let's run debug mode again. So we went north and we're going back west. That is definitely wrong. So where are we? Direction order: northeast, southwest, and we started by going north, right? So let's see. I think what is probably going wrong is that north starts with index 1 instead of 0, and I'm so used to always starting with 0 that it doesn't work. So backtracking is the direction order index. Okay, so let's actually break here. So we are going to direction 1, which is north, and in our direction list that is position 0. Okay, that is correct. So we would get but we get 0. Yeah, that is indeed what it should be. And then our new direction should be 2, which is going to be yeah, it's going to be west in the case of south in the case of direction order. So from direction order it's going to be south. So that is kind of correct, I guess. And then here we have 2 again, and then out of the list of directions that would be direction 2, and direction 2 means hold on. Okay, so that's direction 2 in the list of direction orders, but the opposite direction is actually still going to be taken from the directions. Hold on a second. So this is the index of the direction orders, right? Okay, and then we get out of that direction 2, and direction 2 is south. Okay, that seems fine. And of course for printing I should add another character because we start with 1. Alright, let's run it again. So we're going north, visiting that one, and then we're going to the next step, and it says we're going back south, and that is correct. And so we've seen north, and we are going east. No, we're going west, and then going back east. Okay, we found a wall, and then we're going what are we doing now? I want to break actually at the point where it says going or something like here, and then what we found, maybe like that. Okay, and now we're popping from an empty list, and it's because we found a wall. We found walls everywhere. That is a bit strange. I realize something now, that okay, the robot actually has, it always goes 4 steps at a time. Oh my god, this problem is way more complicated than I realized. Oh my god. Okay, I just had a realization, and it's going to really mess up our whole puzzle. How it's going to be messed up is the following. So let's say our maze looks like this, and it's in the fact that the robot moves 4 steps at a time. Oh, I'm not sharing my screen, excuse me. Here we go. So we have a grid, and let's say here are some walls, here are walls, here's a wall, or maybe let's say that here's a wall, and we have our robot here, and we're moving to the right. It's actually going to move until it hits a wall. Normally it would run 4 steps, so it would go all the way there. That's what I remember from the puzzle, but let's read it again carefully. It doesn't say so here. It moves just 1 step. Okay, then how did I think it was running 4. Maybe I just completely made that up. Only 4 movement commands are understood. They differ in direction but not in distance. A series of commands like 444 would leave the robot back where it started. Ah, I'm not sure why I thought that for a second. Okay. Yeah, no, they just go... Okay, it just goes one step at a time. Wow. Okay, I have to really remove that from my brain right now. So... It looks like something is not going right because we're hitting walls on all 4 directions, which should not be possible technically. And okay, we move 1 step in the requested direction. Yeah. Okay, so we always go 1 step. Yeah. But what we can do actually is run it on the real example. So the real, not the real example, but the example from the puzzle. And the only problem is there is no example. We can only see how it works, and a puzzle input contains the map, and there's no other input that we can use. So we're going to have to find out this way. So we're going to visit 0, -1, and we found a wall, so we're going back south. And does it mean... What does it mean? Do we still use the computer output? No. So from this point it should be safe to actually use the values that we extracted here. So we're going back. But what is a bit strange is that, okay, here we're printing. So if we actually went to 0, -1, we should kind of see 2 positions. We should see the 0, 0 position and the 0, -1 position, but we don't at the moment. And that means that the visited list is maybe wrong. I'm not entirely sure. Let's look at the place where we print our map after the first time. So first we have visited north and we found a wall, and then we should actually get... Okay, yeah, we should get on the y-axis only 1 wall, and on the x-axis we should get 2, I would say. I'm not sure why the range is not... Oh, but we're going north. We are going north. So that means that we should have like a vertical map with 2 cells on top of each other. And right now it doesn't show it that way. So we have our grid and we're saving it to the grid, but we're not actually saving it to the visited positions, and that is the reason why it doesn't look right. So visited is now populated with our position. With our target position. No, wait, I did already save that. Okay, so our visited grid should look like this. It has 2 items, yes. One item is the start item and the other one is looks a little bit different because we're going to change how we're save everything. So our start item should actually keep the first direction in there, and it's 0. It's none actually, because we didn't start there with any particular direction. So I'll rerun it and see that we actually get a 2x2 output. We can get a 2x2 output if we have an empty space, because that one would be a little bit unclear to see. I'm going to use an underscore to make it a little bit more obvious. So we are going to print the grid, and then we're seeing only an @ sign and nothing else. And that is because our minimum y is -1 and our maximum y is also -1, and 0, 0 is not considered here. And that's because we're iterating over the grid and not the visited positions. So visited positions has all the coordinates, and I'm taking xy from them in and returning only the y. And I guess I can actually extract that y positions. So it's just that I shifted from using a grid to using only the visited positions, that it doesn't really go the way it should anymore. So here we have the same issue basically. The y positions and x positions are now saved separately. I must say, in some cases a 2D grid is really handy, but in some cases a list of positions is also very handy. And I think using both of them in the right moments is key to making good navigation code. So, and the advantage of using positions in a list is that you can easily get access to both the x and the y coordinates. So we have found something and we're going to print something. Our min y is now -1 and the max y is that. And now we have actually 2 cells in our grid output. That is the way it should have been. And now we're going south and going back north. And it is a wall. Then we're going west, and afterwards going back east. And what we found is a wall. And then we are, okay. And the underscores are, oh, wait a second. Why do we suddenly get underscores there? Oh no, that's just because I wanted to make clear that we've not explored this position. So I'll make a question mark for that to make it a bit more clear and less confusing. And a question mark, yeah, that means we haven't seen it yet. So now we are there, but we cannot actually go up or down from there because we're at a wall. Okay, right. I was thinking I can check the toVisit list to see if it's actually in that list, and if it is, then make a question mark. Otherwise, I'll just print nothing. That makes sense, right? Because we cannot visit every question mark. So if x and y is in toVisit, then I'm going to print a question mark with no ending. And otherwise I'll print the rest. So let's see how it looks. toVisit, what does it contain? It contains, toVisit is basically a list. So we cannot check it directly like this. Let's see if my music is still playing. No, it's not playing anymore. So 1 second while I adjust and play some other music. I'll just replay it. It was a nice one. Here we go. So if we have not visited it yet, but we want to, then I'm going to save it positions like this so that we can actually quickly look it up. Position for some visited, the list contains the direction and the position, so we can do it like this. And then we are going to see some question marks. That's going to help. That means also that we actually need to check the toVisit list for the max and the min y, but we can also do it a little bit simpler. We're just starting 1 to the left for when we are drawing the grid and 1 to the right. So now it looks like this. This is very helpful. Hi everyone, I see that some more people are coming online. That may indicate that they have solved the puzzle. Did you solve the puzzle, or you're stuck and you're curious how I'm doing it? I'm not exactly stuck, I'm just working on all of the steps that are involved into solving this. And right now we can see where our robot is. It's this little @ sign. And we see the question marks where it still needs to go. So now it's going down, and it's going left, and it's going right. And it found a wall, and then we're stuck. Because if we find 4 walls, of course we're going to be stuck. And yeah, what can we do about that? We can change it into a depth first search, because I'm not sure how that would help. Arcanian Archer, wow, good job finishing both parts. I'll be happy to have you on the stream and hear how it went. I'm still stuck on, well, not stuck, I'm still working on part 1. Slowly trying to figure out why I get 4 walls on each side of my robot right from the start. And it went poorly for you? How so? What happened? Your code is so awful today. Well, you got it done. That's what counts, right? Secondly, to make it nice, but it's not how to say? It's not necessary per se. So we wait for the robot to finish the movement operation and report on the status via an output instruction. And let's see, it can reply with any of the following codes. The robot hit a wall and it didn't change its position. Aha. Aha, okay. Actually, I think that is the key to understanding it. So, how I assumed it worked so far is basically that the robot is going here, and then it finds a wall, and then if it is a wall, we have, yeah, and then we just go back right after. But the fact is that if there is a wall, the robot didn't move, so we don't have to trace back. That means that also our current position is actually not changed, and I have to adjust for this situation. So if we did run into a wall, then please don't backtrace. So if the status is a wall, then we're not gonna back. So if it's not a wall, we're going to backtrace, right? Yeah. Backtracking. Okay. And that means our position didn't change also. And does it matter otherwise? Does it matter what our position was? We're not keeping a grid anymore. So I'm removing the grid. And I think X and Y is used not anymore, only to see where the robot is. So I guess I can say that the robot went to the target position if we didn't hit a wall, for example, right here. So basically both cases are the same. We didn't hit a wall, then we have a target position, otherwise we don't. And then also our map renderer is going to look a little bit more correct. So reloading, and X is not defined, so I am using X somewhere. Yeah, so if we didn't move, it means that we're still at the previous position. And the previous position is... Oh, I was calculating that one before, but now we don't have it. So let's actually keep it in the to-visit list as the previous position. So when we add anything to the to-visit list, we're going to keep the previous location, which was the target position basically. And also here at the start, where we have the to-visit list, we're going to have to append it. So that is 0, 0, the origin. And now we can use previous position in every step, and to say that that's where we still are. So XY is the previous position. I hope that would work right away. That would be cool. Too many values to unpack, so that is somewhere where we are still extracting something that we don't need. This also we don't need. And let's see how it looks. There we go. We're going south visiting and we found a wall. Yeah, so now the question mark is turned into a wall. And then we're going to the west and we succeeded and we found a dot. So we have a good space to move to and we're appending all of the other ones to the list. But in fact we are going back. So now we're going to explore the other side, which is also empty. But of course, if we are going to visit this node right here, we have to be there first. We can't just say we're exploring that one right now. So it sounds like either we are going to have to implement a very complicated way of tracing back all those paths, which may be possible and may not be that complicated. We need to know from every position how to go to the start and then how to go from the start to that particular node. That is the way to do breadth first search. It's so wildly inefficient if it was a real robot, and also in terms of code it is a bit inefficient. But I think we have to do it because we have only one robot. Of course we could make multiple robots, but it's still an arbitrary number of robots that we would try, and we have no guarantee to actually solve it quickly. Right. Okay. So I think I am going to try to move to the start position and then go from the start position back to the target position. Oh man, that means we have to keep a path, an entire path to every position, which we can do. So we have already kept the previous position. Yeah, you wanted to do breadth first search also, but had trouble getting the robot into position as I popped things from the BFS queue. Yeah, so I'm facing that exact same problem right here. And you're popping things from the queue. So yeah, exactly. So either we can just do a depth first search and trace back every time. I think we can do that, but then we have to make sure that we explore every possible position. You know, actually I'm going to commit right now because I've made so much code and I'm afraid to break it at some point. I'll use this trick here to commit a single file at once. Day 15 already, part 1, work in progress. Fuzzy, you've solved part 1. Good job. And also, yeah, it's hard for everyone today. So you use the DFS, which you're not happy about. Well, in that case, I'm going to take the challenge and do a BFS. But I'm not going to be the fastest one, that's for sure. So we are keeping the target position, which is a bit odd because it's kind of the previous position. Let's call it the current position, or just position. Yeah, and you have the same thing. You used a breadth first search, but the code is very slow to run. Yeah, that's the options that we have right now. Yeah, you can't do A star either. You cannot do A star because you also have to do breadth first, kind of with a heuristic, and you can't just jump to any position you want unless you store the robot's position, the robot's data. We can do that, of course, but just overriding the computer with the data that we need. Let's look at what the intcode computer looks like. That is intcode computer. Actually, if we just have a way to save state, export state, and then load state, then we're done. That's not that hard, so I'm going to do that. In Aneurysm, you used both DFS to build a map and then BFS on that map without moving the bot. Oh, that's also interesting. Cool. Right, because you do need to know the number of steps, right? Yeah. Okay. I'm going to keep the state of the computer, so I'm going to get state and that is going to return a tuple, I guess, and it's going to return the output. I'm not sure if output is really necessary. I think positions is necessary, and the execution, no, the pointer, the instruction pointer. And what we need is any input that we might have. Self.inputs, and what do we need as well? There was something else, whether or not it's waiting for input. That is probably not going to be needed, but for now I want to keep it. And we need to make copies of all of those arrays. This is just a value, so it will be copied, and inputs will be copied, and that's just the state. And then we have load state, state like this, and that is going to be, I don't know if you can actually assign to an object like this. Instruction pointer self.input self.waiting for input equals state. Ah, it looks like it's possible. Wow, that's pretty cool. And Arcanian Archer is considering to writing a utility that copies a generator like my intcode function. I suppose if you're using a generator, then copying state is going to be nearly impossible. Yeah. Right, and itertools T only works for generators that don't use send. Yeah, I see. Yeah, so in that case, I am now lucky to have an OOP-based intcode computer. And so for every position, I want to have a state that can bring us from there somewhere else. This is day 14. I need day 15. And let's say that visited will contain the robot's state. Visited. Yeah, so we're... Let's see. Okay, I'm going to keep a separate array actually. Robot states. It will be a dictionary with the robot state being initialized to the computer program after it's loaded. So computer dot get state, and the position is 0, 0. Right, and so the computer state is going to be here. Robot state is states with the current position, or target position actually. Hold on. We need to get it from the previous position, right? Yeah. So that's the state we have, and then we need to load that state before we actually run the code. Okay, so now we've reset our robot to the right position, and that means that we no longer need to backtrack. We don't need to run the code in reverse. And let's see how it looks now. I'm very optimistic that it will work, but I think it's a bit part of my character, and usually I found out that it didn't work as I thought it would. So now we're here, and now we are getting an error because we don't have the previous state, and I think we're not saving the state every time, so we should do that. Robot states with the target position equals where are we going to save the state? I guess we're saving the state only when we have no wall. So that is going to be the computer.getState. Let's call it robot also. Refactor. Refactoring works at least a little bit in PyCharm with renaming variables. And let's run it again. So we're going left, and then we're going right, and then we should continue with the left somewhere on the top, and it works. And down and left. Okay, so far it seems to kind of work consistently. Yeah, it seems to be working. Very nice. Okay. And now we get a crash. No, do we get a crash? No, we don't get a crash. Just something happened on the screen that looked a little bit weird. And now what I want to do is actually see... what do I want to see? We have steps that we're counting. And to visit doesn't contain the steps, but to visited does contain the steps. And if we are done... Well, of course, if we find the output, we can also iterate over the visited positions and trace back how far it was, but I would rather keep the steps. So, how many steps did we reach to get to the visited place here? 0, actually. And visited is... let's see if it is used everywhere correctly. Fuzzy has also reached the third part, the second part of today's puzzle. Congratulations. And we're appending 3 direction to visit and the previous position. So we have... Oh wait, that's to visit. Hold on a second. Just need to make sure that I'm reading it correctly. So visited here. Where is visited changed? It has a status and a direction, and now we need to add the steps. Yeah, and here I'm going to have steps is 0. That was fun. Well, I'm glad you liked it. And it took you also quite a bit of time. And so, what did you get stuck on? And if you can say it without spoilers, that would be great, because I'm still in part 1. So the number of steps is basically the previous location's number steps, previous position steps. Let's see, we don't need the first 2 parts. Like this, and then we're going to add 1 to it. Yeah, like that. And then when we're done, I'm going to actually put a breakpoint here to see how what would happen. And we're popping from an empty list already. And if you would look at the map right now, you would come to the conclusion that there is actually no way out. It's kind of not... How do you say? The map is very small and we can't actually find the goal that we're looking for. And I'm not sure if we're doing it correctly. But how can we check it? How can we check if what we're doing is correct? That is going to be very, very difficult. I am not going to be able to write a new input program. Hi everyone who's joining the stream. I am doing day 15 part 1 and we've gone pretty far. We've come pretty far. We have a visualization of what the robot is doing. You can see it here on the bottom. It's a bit small perhaps, but I hope you can read it. The add sign is the robot and it cannot go up, so it's still at the position where it was, and then it will explore left, right and down. And it's breadth first search. And I'm going down first because it happens to be south before east and west. And then it's going left and right, and then left and right, down. Oh, it looks like it's actually doing a depth first search. It doesn't look like it's doing breadth first search. How is that? So I'm appending everything I find to the end of the array. No, it should kind of be depth first search still. Yeah, it's jumping around. When it's jumping around, it is an indication that you're doing breadth first search and not depth first. So it's exploring, and it looks like it's exploring fine. And I see one thing that we could do is to do a kind of check. So even though we've visited a location already and we know that on the side is a wall, we can double check to see if there's really a wall, and if we get an inconsistency there, then we know that our robot algorithm is not running correctly. So here we we are exploring all of the areas, and then at some point we're running into only walls, and we're popping an empty list. And also what you can see here is that actually our robot is enclosed in only walls, so that is a very sure indicator that the code is not working correctly. So it is actually moving somewhere and then finding a wall where it shouldn't find a wall. And you were just fighting with your utility code mostly. And what sort of utility code was that? There is no way to move diagonally. Indeed, so what I'm going to do is to rerun it and to pay very close attention to the output and see what changed. Actually, I can just run it till the end. Maybe remove the breakpoint and run it till the end. And then just look at the difference between the previous two steps. So here it's already wrong. Here it looks kind of consistent still and it's going down. But as it is going down... Oh, it's actually jumping. It's actually jumping from here to here. And that is not supposed to happen, and it means that yeah, it's very much not supposed to happen. And also this position is not on the to visit list, so it means that I'm really doing something wrong. But so far it did really go correctly until this point. And why could that be? So here it should really just go down and that's it, but instead it says it's going south. You have a 2D panel class with a point subclass to make navigating it easier, but it could use some refinement. Did you find out that the abstractions were actually not helpful and that you're working against the abstractions, or is that just a matter of an implementation that should be improved? I find that sometimes my abstractions are actually going to be obstacles on the way. Hold on a second while I have a little drink. I'm still on the stream. So, do we see any other positions where it's going wrong? No, not really. So here it is. I think I need to have coordinates on the screen. That would help a lot. So I'm going to also print for every row a coordinate, like y, and then we'll make it into a string, y, and we'll right adjust it, rjust, and we'll take 2 characters for it, or maybe 3, with a space, maybe add another space, keep it away from the grid. We will run it again, and no line ending. So the robot is at position 5. That's already wrong. It maybe slowed you down a little bit, but you can understand your code that way. Yeah, okay. Yeah, that's the risk of not making abstractions is that you're understanding your problem in a too much of a low level, and you can easily get confused about positions and values and IDs and stuff. So I find this the most difficult part of programming, of our job, is to find an abstraction level that gives you enough control and enough insight into the problem, but not so much abstraction that you're actually stepping away from your problem and dealing with kind of you know, air castles and objects that don't really map onto the real problem. So here we're going, here we're there, let's see, here we're there. Oh, here it already seems to kind of go wrong. No, we're checking left and it finds a wall. Okay, so that's still fine. And why is there a question mark here? If there's a, how can there ever be a question mark there? There can't be. So at some point here we decided that going down and left is a good idea. Okay, that does make sense, but not completely. So let's go to the first part where we are adding those question marks. So here we are, and here it was probably just decided that there should be a visit, but the robot is already here on the right. So I wanna see here. This is the position where the robot might have decided that these two areas should be explored. And so in the step before, you see that it was only on the left. So it went to the left, but already at that point, the position 2 to the left was already added to the exploration list. That doesn't make a lot of sense. Basically, there cannot be two question marks besides each other. I think that is not possible. So I'm going up all the way to the moment where that happens. And here we add a question mark, okay. And here we add another question mark on the side. I think that is wrong for sure, because we've already been there and we know that it's an empty position. Unless I'm looking at the wrong line. So it's both line 4, and we're at the second position here on the x-axis, and on the left we find that we need to explore, and then we say we're going down, and as we're going down we are finding a wall. Okay, but where are we now? And this wall, where did we find it? And if we find a wall, I have a feeling that the visited positions are not unique. And maybe that's because of this, no, because of this part. We should not add it to the visited. We should not visit it if we have visited it before, and also not if we already have it in our to visit list. And the to visit position is not in the to visit keys. And to visit is actually a list, so we need to actually go over all of the items in the list. That is not so efficient. We have to visit position and we need to visit positions also. Let's yeah, okay, I'll calculate it twice. It really doesn't make a lot of sense perhaps, but I will do it twice to keep the code simple. Okay, now we get some, oh my god, it's a kind of symbol, no? Isn't it a kind of drawing? So now it looks very different also. Here we have a space left to visit, and we are visiting it, but actually we find out that we get stuck there. So this is our map. I'm not sure. I have a feeling that it should represent something. It doesn't look like anything in particular. But again, yeah. But it does look like it's kind of systematic. It's not just random, a random map. So does it mean that actually the, how do you say, this oxygen tank that we're looking for is actually on the map and we've just missed it? Maybe it does mean that. So if we don't have a wall, okay, our goal is 2. That's what the robot should output. But really we didn't go to 2 actually. Or maybe we did actually. Let's run it. No. So we're running all the way till the end, and we don't reach our goal. And the point is, where we have no visiting positions, then we're kind of done. And maybe it's, yeah, here we really should check for the goal, and there's no other way to check it than after running the robot? Okay. Well, I'm going to stop trying at this point. I think I will need to debug the robot's code and see where it's going wrong. I also don't know why. Actually, I don't know why we get a different output after I did this double check. That seems to indicate that the way I added the 2 visit positions is not right. Maybe this is wrong. I'm not sure. But I'm going to stop trying now because I've spent already 2 hours on it and I still want to see how you've solved it. And yeah, that's going to help me a lot, of course. But perhaps Fuzzy or Arcadian Archer or Zarankiewicz Alex has a solution that we can look at. You'll share what you got if you can fix your part 2. So Arcadian, that means... But you have fixed part 2 also. And you broke it while trying to make it not awful. I see. Okay, well you can share code for part 1 if you want. Or are you still working on fixing it? Okay. And you're working on making it runnable. Okay. So a lot of extra cleanup to do afterwards also. So Alex is ready with some example. Sorry, awful code. That's fine. I don't mind. Yeah, the int code computer is there, of course, also, so it's going to be quite long. Thanks for combining that, by the way. That is very helpful. So we are at day 15. Alex. And let's see, I'll just run it first. And I need to fix input as usual. Sorry, slow program, I just saw that. And where's input? I think I need to actually load the input somehow. We're starting here by go vertex, and what does that do? Carrier, okay, I found it. Day 15. Alright, let's run it. Oh, it's still running. Wow. Yeah, okay, so it is a bit slow, yes? Well, that's fine. But I hope that we can see some output, but I guess you do have an output statement somewhere that we can use. How to get home. Yes, yeah, you used. Okay. Oh, it's a lot of steps, and it's going to be a little bit of a puzzle to figure out how it works. But let's go where it's red. So you're doing a BFS from 0, and record the path home. Okay, so you have a distances dictionary with all the distances to every position. And you have a queue, and it's called DQ. And what does DQ do? DQ is a list-like sequence optimized for accesses near its endpoints. Okay. And you're doing pop left. Okay, yeah. So it's the same as I do, but you're using a more efficient data structure for that. And then you're saying, go to that vertex first. And so you need to know where you are. And so where you are is probably X and Y. And then you're going from X and Y to this position. How to get home. That's a function. So first you're going to see how you're going to get home from X and Y where you are right now. And how to do that is to send input instructions to your robot, taking the list of how to get home, and that is determined here. So you're making a list, and you have pre, which contains probably the previous position for that position, so basically the parent node, and then you're updating the position with I think what you're saying here is, so we're now at position XX or XY, and we need to go to the previous position, but maybe that's actually the direction, I suppose. Yeah, okay, pre contains all of the directions. Yeah. So you're telling the robot, okay, just go north or south based on the previous array, and then you're appending that to the list of how to get home. And so now the robot is home, and then you're doing again the same sort of function, and you're just reusing the same function and didn't change the name. So now you want to get from where you are to this other position, and how to do that is to kind of look up also what is the previous position to reach that one, and then doing the same thing. So that's actually quite straightforward. And then you run until you block. That is an internal method of your VM. And once you're done, then you know that the new X and Y position is the position that you passed in the input. So yeah, it's a bit messy, but it's still quite straightforward to follow. And yeah, it's basically a good representation of how you can think about it conceptually. So it's not that bad, I would say. And so that is how it works. You first go to the vertex by going home and then going to the vertex. And then you're going to do 4 things, which is probably checking all 4 angles, or 4 directions. And you're sending the robot to go to that direction, and you're offsetting by 1 because north is 1 and not 0. And you run until the program blocks, and you're taking the first output. And if it's not 0, and I have to remind myself what 0 means. 0 means a wall. So if you are not running into a wall, you're going to tell it to go to that particular direction and run until block. Ah, okay, so you're actually running the code, you're running the robot on every direction rather than... Oh. You're saying this one goes back. This is the one that goes back. Oh. Is that what you're doing here? I to the power of 1. I to the power of 1. But it's not a power, it's an opposite. How does that work? Is it like a logical... Is it an XOR? Ah, it's an XOR. Okay. Interesting. I would like to know how that really works. So let's say we have, you know what, I'm gonna draw it. I know what XOR means in general, but just to see how it applies in this case. So we have north, south, west and east, and they have positions 0, 1, 2 and 3, which means in binary code 0, 0 and 0, 1, and this is 1, 0, and the other one is 1, 1. And so basically you need to switch the right bit. As long as you switch the right bit, then you're going to be able to switch between them. That's what you did. And you did that by doing an XOR with 1. So XOR means, of course, that if there's a difference between those particular bits, then you're going to return 1 and otherwise 0. So your comparison bit is going to be 0, 1 for all cases. And we're going to look at them vertically and see, okay, so here these are different, so we're outputting 1 and otherwise 0. And in the second case, here these are the same, so we're outputting a 0, and the left part is the same, so we're outputting 0. And so on the right you can also do that, and you get 1 here and 0 there, and the left sides are different, so we're outputting 1. And so that's how you can go from one to the other. and also back. That's pretty cool, and it works on both wind directions. That's a very cool trick, and I guess, yeah, you can keep that in mind and be able to reuse that in many cases where you're working with directions. But Alex, tell me, how did you realize that this is possible? Did you draw out? How did you know that? I guess the realization is that you have 1, 2, or like let's say 0, 1, 2, 3, and the realization might have been that the pairs are always the odd and even ones. So basically you're shifting +1 and -1, but you're shifting from even to odd and even to odd. So that's only the right bit basically that is determining whether you're going left or right versus up and down, or left versus right or up versus down. And you're quite used to twiddling, and usually something nifty is possible, yeah. And so in my case, yeah, as I already showed before, what I did was I basically shifted my order. So I changed north and south to be position 0 and 2, and then south and north and south and west and east. And in that case I could just add 2 all the time, so that I could kind of go around and end up here again using modulo. But yeah, I had to make an extra array with those directions in different orders, and that was a bit yeah, weird to do that. But yeah, this works. It's quite a nice trick. So okay, so you're going in the other direction, but why? Okay, so you are doing backtracing even though you have the go-to-vertex function that does the backtracing. Maybe that's what's going wrong in my code actually, because in my code I'm going to do no backtracking at all, and if I'm so what I did, oh my god, there's a mathematical representation of what I did. I'm pretty sure that works. I'll take your word for that. I'm just going to rerun my program with backtracking. It is a little bit of a blind guess because I am not really sure what I'm doing right now. Just to see also what kind of output we get from there. No, it just crashes way earlier, so I think we don't need to do that in that particular way at least. Oh, it doesn't. Okay, well that's fine. Then let's see, so you're running backwards and then you run until you block, and I'm not sure exactly why you have to go a step back. I'm not sure about that. And then you're updating the position to say, okay, from the position where I am now, I'm going to go into that particular direction. So okay. So you're going in a direction, no, you're sending the input, then you're running, and then you're saying update position. But what is update position actually? Oh, okay, update position is just calculating the new x and y coordinate, that's all. Okay, so you know the new x and y coordinate, and if you're reaching the goal, then your OS, that was the oxygen system, equals that one, and otherwise it's, if you didn't already, dist was actually distances, so if you haven't already saved the distance to that position, you're going to save it also with a +1, and you're going to keep track of the previous direction for that position. And that's so simple to reverse it. Wow. And you're appending to the queue. So it does kind of logically make sense. I'm not sure if I can understand your algorithm on the high level and also at the low level at the same time. But it does seem to make sense. And for part 2, oh, hold on a second, this is actually... Okay, so here you have a piece of code that is running, then you have another piece, yeah, okay, so that's part 2. Yeah, part 2 is the same thing again. and I don't know what part 2 is about yet, so I'll just kind of pretend not to see it. Right. And how are you other people doing? Fuzzy, I see that you've already completed your piece of code to share. Thank you, Alex, for sharing your code and again pleasing us with little Python tricks and mathematical tricks that probably not many people know. So Fuzzy, let's see your code. Wait, is this the right one? I'm not sure. I'm gonna have to open it again. Safari also doesn't show me the full address bar. Yeah. So I'm going to copy it from the raw part. Yeah. Dragging it all the way to the left. And making a new file. Fuzzy. So let's have a look. Oh yeah, an aneurysm used both DFS and BFS. So aneurysm, if you have your code ready, I would also like to show it to see how you solved it in 2 steps. That would be interesting to see. And now we're looking at Fuzzy's code, and let's see if we can find input.txt or some kind of txt file. Here it is. So it's day 15/input on my computer. And we're gonna run it. Wow! Oh my god, so that's what the puzzle actually looks like. It's completely different. Oh. I had it draw the map just for you. Thank you. That is going to help me a lot. I think it would. Because it shows me that it's a maze, and I should expect really like things going up and down or something. I have a feeling that I'm actually walking on the walls or something instead of on the empty spots, but I'm not sure. Okay, and I'm trying to read in it if there's anything there, but I don't see anything. Okay, well, I'm still thinking about my own puzzle at this point, but I'm going to have to let that go because in 10 minutes I will finish the stream, and so we still have some time to look at Fuzzy's code. The int code computer will be minimized, and you have a panel class that you mentioned before, which is a dict. Oh, you just overrode the dict function in Python. That is a little bit dangerous. But if you're not using it inside, it's fine, of course. And you have a named tuple. Ah, right, that's something that I haven't used very much yet. It's kind of like in between a class and a tuple. So you have a tuple, but you can name the fields using X and Y. That is very helpful if you already have tuples and you want to change it into classes, and you don't want to write class point with an initializer and some fields and then assigning the values from the initializer to the fields. It's a lot of work, and with this you can just define a class right away. And now you do have to initialize those points using, how does that work? You have to use point with some parameters. So basically it's just still a tuple, but instead of writing it like this, X and Y, you just write point. So that's a very handy trick, and I'm going to try to use that from now on, because especially in the last puzzle for today, I ended up having 3 positions, and I got confused a little bit about what position is really what. And that's the utility code. You need to reorganize a bit, you think. Okay. And the panel, what does the panel actually do? I guess it keeps a grid, and you have a way to dump it. Very handy. I think I'm going to also create a utility class for this, because now it's already like 3 times that we need to display something 2D, or maybe 4 times. And I keep writing the same sort of code all over again, making sometimes the same mistake, like, you know, reading all the min and max in wrong and different ways. So it's very handy to keep it at hand. And you have a way to add. Oh, so you can, what does this do actually? Point add. Oh, okay, so actually you're able to add points to each other. You overriding the add method on point. So even though point is not like a standard class, you can still override operators on it and do very cool stuff. That's very handy. So you can also override the toString method, for example, and you can even make them executable. Very handy. And you're dumping, that seems like a pretty standard way to do it. You're going over the X and Y ranges, and then you're printing the position at the map, yeah, just like the way I do it. And you're printing without any characters, so apparently you don't need to write an empty string like this. You're reading and you have different statuses. You're using an enum actually. And enum is something that comes from Python. You didn't make that yourself. And you have hit wall, moved, and found. Maybe you call it moved, I call it empty. And maybe if you call it moved, it's a little bit more obvious where the robot will be in the end. And if you call it empty, it might not be so clear. So I think I might have kind of confused my robot's position. Excuse me. And this name might help me to figure out where I misinterpreted the robot's position. And you have 4 directions and you have 2 point. Okay, so that converts it into a point. And so super OOP style programming, that means we're now looking at all the classes first before looking at the behavior. A panel item is one of those 3 items, and you made an extra one for unknown, and you're using a space for that. And you have oxygen, empty, and wall like that, and you have a droid. So I'm going to start from the bottom now. So you initialize a panel and you initialize a droid, and the mapping is going to be just the grid basically, and you're going to run your interpreter with the 2 lambdas again. One is what should happen on input and what should happen on output, and then you're running the code. And let's see, droid.sendMove, that is defined here. So if the mapping is complete, you're raising an exception. What is this? Yeah, it's an exception. And otherwise, if you're telling it to move, the last status means that you moved. But if the last status means that... Oh, but how does it work? So send move happens when... when the robot did move. No, when the robot is asking for input, okay. So that means that probably, as you're running the code, that means when output is triggered, then this is filled in. So getStatus is the output function, and that is always ran before the sendMove function. So this we would look at first. So we are getting a certain status event. Follow the left wall. Yeah, follow the left wall is actually the best way, well, the easiest way to solve a maze. I was thinking about that, but I thought that, yeah, I'm not sure why I didn't do it that way. I think I wanted to do it breadth first search, because following the left wall doesn't guarantee that you would find the exit in the quickest way. But it does give you access to the exit, and after that, yeah, you can resolve the puzzle doing breadth first search on your map. Yeah. So let's see. There are cases where it could fail, but the input is designed in such a way that it doesn't. Yeah, it can fail, for example, if you have an island. So for those of you who don't know this maze solving algorithm, it's very simple. Let's say that your maze looks like this, and the thick lines are going to be the walls. Unfortunately, I'm not gonna be able to show that very clearly. Maybe I can show the page as I see it when I zoom in also. Yeah, okay, now I can draw big walls. So let's say you have a wall here and a wall here. Like this. And you have a wall here and a wall here. Okay. And your robot starts here, and your exit position is let's say here. Then I need to make sure that there's only one exit, of course. Then what you're going to do is always follow the wall on the left. So the robot is now on the bottom, and let's say it's facing this way to the left. Then in that case it's going to trace this wall and here and here and here and here, and then reach the exit. That works. But there's one case where it doesn't work, and that's the case where you're actually on an island, as it's called in this particular problem solution. So if you're tracing the left wall here, you're just gonna go round and round and round and round forever. And so Eric Wassel did us a great favor by providing us input that doesn't have it. And how can we know for sure that there is no island on the map? I'm not sure if it is obvious if you just look at it quickly. I guess it takes a bit of effort to generate a maze that doesn't have islands. Oh yeah, I know how to generate a maze without islands. It is basically you draw all the walls, and all the walls must touch another wall. So you can guess, and if it doesn't work, try something else. And that's of course another way to do it. But if you start with a wall and then you draw every wall from another wall like this, and then this and this and this, and then no matter how many walls you're going to draw, you're never going to be able to draw an island. So that's one way to do it, I guess. And another way to do it would be that you start with a completely filled in solid, and you're going to remove things from it. And you cannot remove a piece of wall if it would connect to an empty spot right away. So you cannot go here. So you go here, and you can remove this piece because it's not connected. It's connected to 3 solid walls, but you cannot go here because that piece was connected only to 2 solid walls. And if you do that, then you would also never generate islands. Alright. So you say here that when you get an output, then you're going to see what you're gonna do next. Let's see, so if you hit a wall, you're going to keep it in your map. If you moved, you're going to say that it was empty. So I like how you have a different status for moved and empty, even though they are kind of very strongly related. And you have moved and found also. That means that you have oxygen in your target location. And let's see if the locations are actually the same. Yes, they are the same still. And you keep the oxygen location. So every time that you have an output, that's what you're doing. And after that, the robot asks for an input again. Well, I guess you have to run the robot again. So let's have a look at the time, by the way. I'm going to end in a bit after we go through the parts for part 1 of Fuzzy's code. Yeah. Am I still in the right position? So here we are looking at the places that we need to visit. Hold on a second. I think mapping complete, that is the whole first step. That is a very big step. So every time we get the status, how do we make sure that we keep running? Do we provide input? Maybe we do. Oh, I see. That's actually what's happening here. So lock is the new location where we're going, and when we need input, that is going to be here. So if you moved the last time, then you're gonna go left, and if you moved and found, also left. Otherwise we're gonna go right. Okay. and left will just do a -1 turn, and a -1 turn means the computer calls to get status and send move commands when it needs them. Yeah, so it always asks first for a turn and then gives output, and then will just automatically ask for another input. So you don't have to kind of make sure it keeps running, it would just run by itself automatically. So to turn left, you're using a list of directions, and you're kind of going to the next one, but you're modulating it to make sure you're always within bounds. You're wrapping around, and you take the last move index. You take also the last move's direction. Move would be, what would that be? Move is actually the index, and then the actual direction is something like this. And you've also changed the order to be able to do some easier way of turning, I suppose. And okay, when the mapping is complete, that's after we send a move, we check if the mapping is complete. And how do you know? You know if there's no empty spots left. And oh no, wait a second, you're checking everything. If there is something that's not an empty spot, and it's not oxygen, so it's a wall, then you're continuing. So it's a wall, or you moved to a wall. And each empty spot has all 4 neighbors seen. Ah, okay. Hey Anthony, welcome on the stream. How did it go for you today? Usually I'm finished by now, but today it's really a long puzzle. You got points. Congratulations. Awesome. Is that the first time you got points, or did you manage to do that before? Wow. Let's look at the statistics. How many people have solved the puzzle so far? Oh, that means that you're actually one of those people who solved it very quickly. I looked at it at half an hour of time, and there were only like 200 people, which is of course more than the leaderboard contains. So that means you were even earlier than 30 minutes. Quite a good job. The third day you've gotten points, and you got points for 5 parts so far. Nice. That means that is a very good job, but then probably you're not going to be on the leaderboard with just 5 parts. I think you need to really kind of finish every part and be quick every day to stay on the board. Yeah, that's not enough, right? Yeah. I have 0 points so far. I haven't solved anything faster than other people. So I'm not exactly sure how this works. I think you're checking all directions and see if you've checked all the directions. Nubali finished part 2. No, part 1 that is. Good job, congratulations. It's a nice show of dedication that people still finish it after 3 hours of work. And you're not going to be doing the 18th plus till January. Yeah. You know, at this point I'm not sure if I'm able to kind of keep doing all of the puzzles. They are getting really hard now. Well, yesterday was fine, but this one is really quite a big one. So if the direction that you're checking right now is not in the mapping, then you're not done. And otherwise, if you checked all of this and you didn't return, that means that you're done mapping. Okay, and then once you're done mapping, then you can actually show it. Okay, and then you can also do a breadth first search on your generated map. Holidays are starting, yeah. But even if I wouldn't do live streams, I would still like to finish all of the puzzles. So I would do streams, but maybe not at 6 o'clock in the morning, and maybe not on the day itself. Arcanian Archer is done fixing part 2. But I am not gonna have time to look at your code today. We're almost 2.5 hours into stream, so I would just go through this breadth first search mapping by Fuzzy, and that will be it. So you are keeping a list of distances and which ones you have to do still. And while you still have items to look for, you're going to pop the first one, and the distances are going to be read from the distances dictionary, and then you're going to check from 1 till 5, and you're going to do the others, make another spot, and that one is your current spot plus the direction you're facing right now. And then the kind is what you're reading from the mapping, and you have a default for that, which is unknown. And if the kind is empty or it is oxygen, then you're going to do to see if the other spot is not yet in your distances, so whether you visit it or not. You haven't visited yet, or it's actually further than your best spot so far. So if the other spot is actually further away than the other one, then you're going to override it, I suppose, and you're going to count it. And you're also going to append this particular spot to your list of new visiting spots, and you're looping that, and that is it. Man, Dijkstra algorithm is actually quite simple. I mentioned it before that I think I should remember it. I think I'm getting the hang of it now by doing it like from the top of my head, slowly and quietly. But the next time I'm going to do it, it's definitely going to be easier. So it's called Dijkstra's algorithm, but isn't it just a breadth first search? Is it different from breadth first search? That's a question I have. Maybe someone could point that out. And then in the end, you're printing all of the distances to all of the, no, to the particular location that has the oxygen in it. You implemented int code in yet another programming language. And which language is that? Well, if it makes you sad, then why do you do it? It's a modified BFS to mark the distance to each location, yeah? So you mark the distances and that's it. Okay, yeah, I know that Dijkstra is a pathfinding algorithm that is guaranteed to find the shortest path, but it is not guaranteed to do it optimally. It might explore a lot of kind of bad locations, but since all of our steps are always one long, then this time it is it doesn't matter. Right, that's what I was thinking, that you need to take into account the step sizes. Yeah. Okay, let's run it and see. Oh yeah, we already ran it, and that's what you get. And then there's part 2. I'm just going to have a look at part 2 and see if I can figure out what it's doing. We're printing the number of steps. And what else are you printing? The distance. For part 1, what did we actually have to provide? The number of movement commands required to remove the repair droid. Okay. And then here you have steps, and it's another one. It works by using a heap to store the unexplored vertices together with the shortest path found to them so far. So it is a heuristic, yeah, I remember now. So Dijkstra's algorithm uses the path cost so far to continue exploring with the path with the lowest cost so far. Yeah, exactly what Alex is saying. And the difference between breadth first and Dijkstra is that breadth first will just continue exploring the path with the least amount of steps that you've taken so far, and it doesn't take into account the size of the steps or the path cost. So Dijkstra is looking at the path with the shortest total cost and continue exploring from there. And then you have A star, or A rather. The A algorithm is the search algorithm where you're not only looking at the current path cost, but also predicting the path cost to your goal. This is sometimes not possible. In this particular puzzle, it's not possible to know how far you are off from your goal, because we don't know where the goal is. We actually have to like search in the blind, try everything. But In some other cases, you do know where to go. For example, you know that your goal is in position 100, 100, but just the path to it is what you need to find out. And in that case, you can predict how far you still need to go. If it's a 2D grid, for example, now my AI studies do come in handy, finally. Let's say you have a 2D grid and you have some maze like this, and this is your target and you're right here. Then, or let's say you're here at the moment, then you can estimate the number of steps you need to take by just taking the Manhattan distance, because you don't know all the walls that are here. You haven't seen them yet, so you cannot make any estimate based on the walls like this. That would imply that you already know the map and you know the solution. So you can just assume the simplest case, and the simplest case is that there are no walls at all, and then your cost is going to be at least the Manhattan distance, so that would be like 3 and 2 equals 5. And now there is another algorithm that is even better than A. It's A star, and it has to do with your estimation function. And the requirement is that your estimation function is always overly optimistic. And that means that you're going to say that if you have a few options, for example, your options to explore are, I'll use a different color for that. Your options to explore are here, 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 and here. And you're going to estimate for each of them what the total cost is to reach the destination. And the tricky part is the estimation for the part you need to explore. So that's this one, this one, this one, and so on. And now if you now here's the thing, which with A star I always forget if you should underestimate or overestimate your solution. I think you need to underestimate it, so you're going to be always overly optimistic. Why is that? Because let's say you reach the target, so you're here, and here you've reached the target, and you know that the distance from that position was 1. But there might be okay, that doesn't make a lot of sense, because here we're dealing with single steps. So let's say that we're here and we can go to here, and we've reached the destination and it was 2 steps, but actually in this particular maze there is a teleport that can let you reach it in 1 step. And now if our estimate for the right position here was actually going to be 2, which makes sense, right? Because it's 2 away, maybe even 2 plus 1, because it's 1 to the right. That means we estimated it as 3, and we would never explore that option. But if we can, we would not explore it because we think, well, it's going to be at least 3, right? So, and we already have one that has 2 as a distance, so it would never make sense to explore this option. But it's incorrect. So you need to make sure that your estimation function is really the minimum, but an overly optimistic estimation. Fuzzy, you're saying I ought to pop my leaderboard on there while you've got a crowd. Do I have a crowd? Oh, I do have a crowd. I didn't realize that. Wow, that's funny. I think that Anthony Wright's code just raided me, and I have no notifications for that, so probably thanks for the raid, Anthony. I was gonna raid you back because I'm going to end my stream in a moment. I'm just going to finish this little explanation, and then I'm going to call it an end for today. And so the leaderboard, yes, I do have a crowd, so I'll show it right now. So you can see right there, I have a leaderboard, and you can be on it. And the code for that is, just looking up my code, and I'm going to paste that in the chat. If you join the leaderboard with this code, then you're going to show up on the stream, and do send me a direct message with your Advent of Code name, so that I can make sure that the name on the leaderboard is the same as your Twitch name and that people can recognize you. Some small features you might not know about: if you solve the puzzle, there is going to be a gold star shown on the screen with your name, and I will announce it to the people who are watching. And so we can also keep track of who finished the puzzle and which part. And your particular score for the day is shown on the right of the leaderboard. So behind every name you see how much points they earned that day on our leaderboard. So we were talking about A-star and the particulars of A-star and how it is different from a normal A algorithm, which is guaranteed to find the optimal solution but not guaranteed to find it in the shortest amount of iterations. And so what happens if we make an... I see something is a bit wrong with my iPad stream. There we go. So if we make an estimation that is a little bit optimistic, so let's say that we estimate this one, which was 3, but we estimated it to be 2, for example, then it means that we have a solution which we know for sure is 2, that's this one, but there is another one that is 2, but it might be smaller. No, how does it work? Yeah, it is 2, so it's an equal solution. Okay, so we have to be even more overly optimistic to explore that alternative. So let's say we're so optimistic we think it might be 1. That means we're going to explore it and we find out that it's actually 1. So keep that in mind, that to make sure that A-star is going to find the shortest path, always be very overly optimistic, but the more you're close to the actual distances and costs, the better your A-star algorithm is going to perform, because if it's so optimistic that it wants to try out every solution, that would happen if you say that if your estimation function always returns 0 basically, then it's going to explore every solution. So your estimation function has to have a good correlation with the actual distances, but it should never overestimate it, because if you overestimate an option and it was actually a shorter path to the goal, then you're not going to explore it and you're not going to have the fastest, shortest path. So that was A-star in a nutshell. Thanks everyone for being on the stream. If you did like what you see, and if you did like the way that we discuss the problems together and we go over people's code, if you want to share what you've made on the next stream for day 16, then please do subscribe and check in after you solve the puzzle, and we can have a chat and explore the different ways of getting Advent of Code done. I hope you've been enjoying Advent of Code so far and that you're going to enjoy the rest of the days. Good luck with all of your puzzles, and also have a very Merry Christmas. See you.